Hello, welcome to this video. Today, I think I'm going to do a little bit of discussion about Kirchhoff's voltage law. You know what, I've changed my mind. I'm going to do the current law today. Current law. KCL. Yeah, Kirchhoff's current law, that's KCL. I realize my last video didn't have an episode title on it, at least on the paper. That's because I recorded episodes 2 and 3 at the same time, and then it was just so long I broke it up into 2, but I'm going to keep trying to continue to do this moving forward. So before I can talk about KCL or KVL, I really need to introduce the concept of an electrical schematic. And without loss of generality, I need to introduce the concept of a circuit element. So what to do? Let me start by drawing this symbol here. Okay, in the beginning, so that we stay as general as possible, I'm going to use this rectangle, this plain box with these lines, and then if drawn independently, I'll put these little dots on the end. I'm just using this symbol to represent a circuit element. Now this could be anything. And there's a lot of different kinds of circuit elements that have their specific symbols to identify them, but because that's not the point of the examples I'm trying to teach right now, I'm just going to keep this as general as possible. If you know a little bit about electronics, you know that in Europe they actually use just this plain rectangle to represent a resistor, but in this case I'm just using this to represent the most general case circuit element that I can. Now in any case, when you see a circuit element drawn on its own like this, there'll be some symbol in the middle here that represents what the element is, and then there'll be these lines coming out on either side of it. And then sometimes you'll see people put dots on the end. You'll see people, sometimes they fill in the dots, sometimes they leave it just a circle like this. I tend to draw it this way just because that's what I'm used to. And in larger circuit schematics, anytime you have something unconnected like this or sticking open, usually people put a little dot on it or something, and then there'll be labels everywhere just so you know it's intentionally unconnected or just so it leaves a convenient place to label a current or a voltage or something like that. So just so you have your bearings about what we're talking about. Now I think what I'm going to do is just draw a very simple circuit and then talk a little bit more about these lines and what those mean. Okay, let's draw a little circuit, and even this I'm going to keep only partially drawn. So let's do this. So here I'm not bothering to draw the rest of the circuit. I'm not bothering to close these loops. I'm just doing these little dots off to the sides to indicate that there's more to it than this, but it's okay for us to analyze just this one section of this circuit for what I'm about to talk about. So, based on what I just said, I've got these little dots here showing that these go off and connect to other things, and I've drawn these rectangles just to indicate that there's circuit elements here, and it doesn't matter what they are. I'm just trying to keep this general. So the last thing I feel like I should talk about is what does it mean when we draw these lines between these circuit elements? When we connect things like that, what rules are we playing by here? And the thing to remember is that this is a schematic, and usually in schematics it's to be interpreted as the ideal case description of your real life circuit, meaning it's the theoretical plan or it's the ideal circumstances under which your circuit would operate. And what do I mean by that? Well, if it's kind of like if you had planned for there to be a light bulb and a battery, you might draw a schematic where you have a symbol for a light bulb and a symbol for a battery, and then you would connect them with these lines to indicate that they're connected. But those lines, these lines that I'm drawing between the circuit elements, don't exist in the real life circuit, meaning they're not modeled. I'm not capturing, so in real life, if you have a battery and a light bulb, well, what really connects them? You've got wires, most likely, right? And those pieces of metal, those wires, usually we just approximate them as ideal conductors because they're very close to that. but in reality they're not. They're non-ideal in some way, in that they have a tiny little bit of what's called resistance, which I'll talk about coming soon, and other physical properties that play into it. And so in real life, you know, they're not just an ideal connection. There is something there, that wire is itself a circuit element that if you wanted to be totally accurate, you would model it in your schematic with its own symbol of a circuit element here. But in most simple circuits, especially at DC and low frequency AC, we make a lot of approximations because the error or the approximation delta is so small that it winds up not really mattering. So if one of these circuit elements is a light bulb and one's a battery, they might actually be connected with physical wires, right? And so we're drawing these lines on paper to represent the fact that they're connected electrically and that there's current flowing through them and that there's associated voltages. But what we're not capturing in this circuit is the physical things, the physical objects or materials that are connecting these elements. And that's okay. So I guess for the purpose of this drawing, what you need to remember is that I'm just indicating with these lines that these things are connected, and we're going to forget about the rest. It would be like in real life if that light bulb was just sandwiched up against that battery and there was no wires between them. It was just a direct connection between the battery and the light bulb. That's what this is. That's what we're saying here, or we're modeling it as that because the wires are close enough to ideal for all intents and purposes. Okay, now with that out of the way, when you draw lines like this to connect circuit elements in a schematic, they're basically behaving as ideal conductors. And so what's an ideal conductor? Well, an ideal conductor is a circuit element or a material that has no resistance. And again, I guess I'll talk about resistance in a later video, but another way to think about it is that a conductor in your circuit, as current flows through it, has no voltage across it, ideally. Okay, a perfect conductor, which they don't exist in real life, would have no voltage across it despite the fact that current flows through it. And I know that sounds a little weird, and I said some things in the video about voltage that appear to contradict that, about how anytime you have current flowing through a circuit element, there's a voltage across it. And that's true except for the case of the ideal conductor. But lucky for us, I don't think there's really a contradiction there, because ideal conductors don't exist. We fabricate them in our analysis or our schematic modeling just to help us out and simplify things. So these wires are acting as ideal conductors, meaning that they're allowed to connect these lines, or these wires are allowed to connect these circuit elements. They're allowed to have current flow through them and pass through them, but they don't affect the performance of the circuit in any way because there's no voltage across these lines or across these wires. And okay, you might be thinking like, well, I wasn't assuming that anyway. And yeah, maybe I just wasted a bunch of breath. But it is a very important distinction, and later down the line, we'll no longer accept this notion of ideal conductors in our circuits, and we'll start modeling everything. We'll model all non-idealities. But I think that's way down the line, but I just wanted to capture this here for sake of argument and understanding. Okay, now to nail down a little bit more terminology before I jump into this, something that's convenient, a word that's convenient to use when we start talking about current and voltage analysis is a node. So what's a node, or what's a circuit node? And I guess the easiest way to say it is it's just any point where two or more circuit elements connect. So this intersection here where these three elements come together, people might call this a node. And sometimes when it's a spot where more than two connect, people will draw this little dot right here. And they do that just to indicate that these are in fact connected, because sometimes when schematics get really crowded, you might have dozens of elements and wires and lines running everywhere. And it might not be clear whether or not two wires are supposed to be connected if they overlap, per se. So for example, if there are two lines that overlap, a lot of times people will draw a little dot there just to make sure you understand that, yeah, those are supposed to be connected. And some people, there's different conventions. Sometimes you'll see this, sometimes you won't. Sometimes you'll see lines overlapping and there's no dot, but they are meant to be connected. So it's just, it's up for you to decide and figure out, or talk to the designer or whoever drew that schematic. And once you learn that person's convention, then I think it'll be fine. But I find that if you just follow this convention of putting a dot, usually it's more obvious, although I think sometimes schematics can start to look a little weird with these dots everywhere, and I think it's just in your best interest to try and draw schematics without overlapping lines if you can, just to avoid all confusion. So okay, with that in mind, we've got this intersection of these three elements, and we're calling this a node. And now I'm at a point where I can introduce the definition of Kirchhoff's current law, or the actual rule here. So let me just write this out, KCL. The net current entering a node is 0. Now the important takeaway from this law is this word right here, net current. And kind of the theme that's going to carry into this video, or the concept that carries into this discussion kind of from previous videos, is all of this analysis hinges on this idea of reference polarities or reference directions. So for net to make any sense, I guess what you're talking about is if you have a flow of current or a flow of fluid, you've got flow in certain directions and you have flow in other directions, and if you add all those things up at a certain point or a certain reference plane, you'll have a net current or a net flow at that point. And what KCL says is that the net current entering a node, or so the net flow of current at a node, is 0. So if you interpret that as, if you look at this node, you have a current entering or leaving it from each of these elements. And so let me draw that this way. And now the interesting thing about what I've just done is I've drawn all these arrows pointing inward. But they don't have to be pointing inward. I could have drawn them all pointing outward, or I could have drawn some of them pointing in different directions. Any combination of these arrows pointing in this direction or the other direction is appropriate here, because all the arrow means is this current positive or negative with respect to this node? And that's up for you, that's up to you to decide. So anytime you look at a node like this, it's up to you to decide the convention with which you want to count this current. So you can just say, okay, current that actually comes into the node is positive. Or you could say current leaving the node is positive, but whichever you pick, current flowing in the other direction has the opposite magnitude or the opposite polarity. So if this is IA, and this is IB, and this is IC, what KCL says, if I'm going to define all these currents pointing in this direction, and then I'm going to say, okay, let's say any current entering the node I'm going to count as positive, well then KCL says that the current entering the net current entering the node is 0. So you can pretty easily see how KCL really gives you this, IA plus IB plus IC equals 0. So one of the first things you might notice is that either there's no current flowing at all, or one or more of these currents doesn't actually flow in the direction of the arrow that I've drawn here. And if you realize that, then good, you're keeping up, because really all KCL is an extension of the law of conservation of charge. See, current is just an extension of charge. And so to say that, oh, current into a node is conserved is essentially what this says, isn't anything new. There's nothing special here. This is just conservation of charge. And so what it's saying is, if you actually couldn't have all these currents flowing in the same direction, because where would they go? Like I said, current has to flow in a closed loop. And if I said that there really were 3 currents pointing in the same direction like this, well, what happens to all the charge? This is just charge. So that you'd have charge entering the node from all 3 sides, and where does it go? It can't just disappear in the middle here. So all we're saying is this charge has to go somewhere. So any charge that comes in from IA either has to leave through IB or IC. And then you could say the same about either of these other currents or charge differentials. And so in that case, so you can draw this. You can draw all these currents pointing in, right? And you can write out this expression, and this is true, and you can say this is true, but what will wind up happening is that you'll see that one or more of these currents is actually negative according to the reference direction that we assigned to it at the beginning. So in order to figure this out, you'll need at least some amount of knowledge about the circuit, whether it be a value of one of the currents, or one or more of the currents, or knowledge that one or more of the currents are equal, or something. You need some relationship about one or more of them to deduce the reality of the other currents. So for example, in this case, let's say I knew that IA and IB were equal and were actually both flowing inward. So if IA equals IB, and let's say they're both greater than 0, meaning they're positive currents with respect to this reference direction I assigned, meaning they're both actually flowing inward, well then based on this algebraic expression, we know that IC equals minus 2 IA equals minus 2 IB. And all that minus means is that IC actually flows in the other direction. It's negative with respect to the reference polarity or reference direction that I assigned earlier with this arrow. And the 2 comes from the fact that it must be double the size of A and double the size of B, because I said that A and B are equal. So I could just write IA and IA in both places, and it sums and doubles and flows in the opposite direction from this arrow, giving you that IC is minus 2 IA. And so this convention that you need to keep track of is really simple. Like Kirchhoff's current law is just addition or subtraction, and it's just counting charge, and it's as simple as keeping track of your reference directions and polarities. And as simple as it is by far your most powerful tool for circuit analysis in electrical engineering. You will use this every day for years to come. If you ever get a job in electrical engineering doing electrical design or circuit design at a high level or a modern industry level, this is something that you will do every single day. If you pursue this in your undergraduate studies, this will happen in near every class. Any class with circuits, you'll use this every day. If you pursue your studies at a graduate level, you'll use this every single day. And you'll use it to analyze extremely complicated circuits, but still this very simple fundamental law or rule or strategy, whatever you want to call it, this is the basis for everything we do in circuit analysis. Once we're no longer concerned with what these elements are, and once you've learned what they are and how they behave, this is what you will use to analyze these things. And you'd be surprised just how crazy and complicated these circuits will get, but you can still always fall back on this simple postulate. Okay, I want to say thank you for watching this video. I hope this was helpful. And I know this was just kind of a very quick or simple little example, but I hope this did the trick. I mean, let me know if you want to see more examples of this, because I can do a video where I just compile one or more examples and show maybe a more real or more complete circuit, or maybe I'll wait until I introduce circuit elements specifically and talk about or at least get more specific on circuits before I do more specific examples. So anyway, I think the next video is going to be KVL, Kirchhoff's voltage law, so tune in for that, and leave me any feedback that you think would help you out. Okay, thanks.